lesson. So we got 8 people logged in. That's not a bad turnout for a class of 12 to 15. I'm not judging. I don't expect everybody to make it every time, but I applaud you who do. So we'll now go to our lesson collection and take the link, and it should have this web link, and that's still not working right. All these links are good. The cascading style sheet isn't rendering correctly. And try to reload it just once. No, but it's not going to work. I'll deal with that because I personally prefer the look and feel that I've programmed into it years ago, and I don't like it when it just is a boring old web page. But we have the usual readings: EPANET by example, hydraulics of pipelines by Werbs and James. And in fact, 2 of the examples we'll present today are not derived, they're taken flat out of this particular book. Pipe networks by Chin, our usual water distribution system, some various software links, and these video links currently are not activated, but they will be by tomorrow. And so today's lesson is actually examples. Oh, cool. Let me go ahead and fix that while I'm here, and we will. So it's not examples 1, 2, and 3. We're doing examples 4, 5, and I'm wondering if my naming system is 6. So example 4 is network with fixed grade node supply, which will be very similar to the network that you'll build in the homework. Example 5 should be a simple pump. Stupid name. It's a simple pump example. And example 6 is network with a fixed grade node supply and boosted supply by pump. Okay, so that will at least bring that up to date. And now we have the correct examples, and it's in this data in the lecture EPANET file. So example 4, 5.1 and 5.2. So I was not actually 4, 5, and 6. And because I'm anal, I will go ahead and actually do it correctly. There we go. So let's take the lesson notes link, and we're going to look at the PDF. Ostensibly titled Pumps in EPANET, but really it's just continuing the network modeling tool by example. And at the end of this, you will have seen all the necessary parts of EPANET to do most of the next exercise, which is not uploaded yet, but it's going to be working with the network that you've already found elevations for and node demands for. So that'll be our next step, is to build that into the tool. So as a brief overview of this lesson today, we're going to look at 3 examples. First, a network simulation without a pump, and we'll go through the application of the modeling protocol that I suggested in our last meeting. Then we'll do a pump simulation, and this is a very simplistic and contrived problem. Its purpose is to illustrate how the requisite data is prepared and entered for pump simulation. And then the last example, we'll do a network simulation where there's a pump. And the network in the last example is really just an extension of this first network. So here's our first network. So we are asked to compute the discharge in each pipe and the pressure at each junction node for the 8-pipe system in this diagram here. And somebody has already drawn it in a very schematic fashion, and that's all that's necessary for these kind of analyses. Make a solution in EPANET, report the results in US customary units, identify the node with the lowest pressure, and we can ignore the transmittal letter part. So this is from a while ago. So if we recall the modeling protocol summarized from the last meeting, I suggested that an effective way to answer questions like that would be to sketch the layout on paper. And I've already mentioned that you would sketch it, provide the other information, then you can actually load it as a graphic into the software tool, and it will give us a visual reminder of the pieces we need to make an effective hydraulic simulation model. Identify the pipe diameters, their length, and the appropriate roughness values. Identify node elevations and demands. And those two critters, you should name them too. So come up with names for the pipes. And they can be silly names like Pipe 1, Pipe 2, or Fred, David, Judy. It doesn't really matter as long as you can tell them apart on the layout when you enter it into the program. And then identify and supply reservoirs or tanks and the pool elevation for those things. And lastly, if there aren't any, identify pumps and prepare pump curve and problem units. That's not a trivial statement, because often I have put pump curve in different units and ended up mistakenly converting all the problem units to satisfy the pump curve, and realized that's really stupid. Because to modify a pump curve, I at best only have to change 6 numbers, 6 unit conversions. If I have 100 pipes, I got to make 100 unit conversions. So that's really stupid on my part. So to save you from having to repeat that stupid act, don't do it. Put your pump curve in the problem units. Whatever efforts involved there is small compared to try to parameterize a network because of a unit issue. And next, sketch the layout on paper. So here's the layout already sketched, and we'll import this graphic shortly into the program. Actually, I have it preloaded there, but if you had to import it, I could show you how. And then we have to identify the pipes, their diameters, length, and roughness. So in this case, here's the pipes labeled pipe 1 through 8. The length of the pipes in feet, 1 through 8. The pipe diameters in inches for pipe 1 through 8. And this particular example is taken from Werbs and James is an older document. And in their document, they provided friction factor as the entry point for making hydraulic calculations. EPANET and similar computer programs don't actually use the friction factor as an input value. Instead, we provide absolute roughness heights of the pipe material, and friction factor is ultimately computed. So we'll use either a value of 1 or of 0.26. We'll specify the Darcy-Weisbach head loss model, and we can ingest these roughness values in an attempt to match the supplied friction factors from this example problem. Generally, one cannot get them all to match. There's a historical disconnect in the older stuff. They're not wrong. It's just the EPANET curve that estimates friction factors gets horizontally asymptotic quicker than you or I would looking at a Moody chart. I would argue that it has very little impact on the ultimate hydraulics, and so it's not truly a problem. But you do need to be aware of it if you're trying to match stuff against older solutions. Older meaning 20 plus years or more. And then we also have to identify the nodes. So here we have the nodes labeled 1 through 6. The elevation of the node, it's labeled here as ground elevation. So either the node is underground or we'll just use the ground elevation as a good approximation of what the junction elevation would be in the field. They would differ by each other by perhaps as much as 6 feet. So perhaps node 1 is really at 164 feet elevation, but we can use the 170. That'll be close enough. So we have the node elevations in feet, and then we have the demands per node, in this case expressed in gallons per minute. So if we were to add a pump to this system, we would want the pump curve to be in units of feet and gallons per minute, and not units of feet and cubic feet per second, which is also typical. And then lastly, we have a supply tank in this model, and in this case, we'll have pipe 8 is supplied as 300 feet, and we can consider 180 of that feet gets to the bottom of the tank, and the bottom of the tank itself is 120 feet in the air, and the pool elevation is 315. And in this particular first example, most of this information is irrelevant because we're not doing extended period simulation. So the ability to keep track of the water depth in the tank doesn't matter for a strictly steady state simulation. So it's going to use a water level of 315. And it's going to treat that as if it's fixed. So in this first instance, even though we'll supply the information as a tank, the program will more or less treat it as a reservoir. And there are no pumps in this case, so we could then start to build the model. So here's a screen capture of it, and let me go over to the software and we'll go through those steps one at a time. So when I run the software, I'll build a few parts of the network, and then I'm going to cheat, and I'll actually load in the network file already built in interest of saving time. So I'm launching my EPANET program, and I'm going to, we'll go ahead and we'll make a, I guess we'll make a new one, and I want to load in the backdrop, and I'll use the backdrop to help me get to the correct directory. That's not it. There we go, and we'll use example 4, which is the wrong one still. Let's try again. See, view, unload. Must be 5.1. There's our base map. And so from this and from the tabular information, we could start to build our network model. So generally, we would start with nodes. Let's make them big enough to see. It should be big enough to see. 1, 2, 3, 4, 5, 6. And we would want to construct our model so that the node names in the picture agree with the node names in the program. The program automatically starts numbering from 1, so these nodes by default will have the correct numbering value. The next thing we would do I've left the tank off for the time being. I think I'll do that almost last. I'll do it now. Next thing we want to do is connect everything with pipes. And we would try to follow the same convention. Get the pipes joined the same way and make sure that they're picking up the correct numbering if I pay attention to what I'm doing. So this is pipe 2. Here's pipe 3, pipe 4, pipe 5, pipe 6, pipe 7. If you're involved with doing an initial design all by yourself, you can probably draw and name things the way you want. But if we're doing an analysis on an existing network and perhaps we're just adding a few pieces to it, then we do have to take some care in keeping track of the naming convention for both the new nodes and the new pipes that we add. And pipe 8. So again, I will check that the naming convention is correct. And if I unload my backdrop, there's the network. It's really not that elaborate. What we would do next would be to systematically go to each junction and supply its elevation and demand. And we want to put demand in gallons per minute because that's what the problem statement says to use. And so, for example, I'll just do node 1. Node 1 is at elevation 170 and its demand is 500 gallons per minute. So in this block, we'd enter a 170. Elevation, we'd enter a 170. And for demand, we'd enter the 500 gallons per minute. And then we would repeat that for each of the nodes, entering the correct value for each of the nodes. Likewise, for a pipe, we'll just do pipe 1. Pipe 1 is 4,000 feet, 10 inches, and it says use point 26. So we would go and enter its length of 4,000, its diameter of 10 inches, and its roughness of 0.26. And let me show you something that's kind of cool. We can move to the next pipe simply by clicking on it, and we have access to the next pipe's database. So we would repeat that data entry process for each pipe in the network, again referring back to the table or our handwritten notes until we have parameterized all the elements of the network. The last thing we would parameterize is the tank, which I think is at elevation 315. And we can go back to our picture and get the other parts. So the base elevation is 300. Pretty sure minimum level goes here at 300. Let me check that. Minimum level is this distance, so it's actually 120 plus the base elevation of 180. So tanks are a little different than reservoirs. There's a little more thought that has to go into it. So the minimum level is 300. That's not right. The minimum level is 120, so that adds up to 120 plus 180 takes us to the bottom of the tank. So 120 plus 180 takes us to 300, and then the max level is going to be 135. And I hope I got that right. We'll know in a second when we try to run it. And that would be the tank data entry. And assuming all the data are entered, we'd be ready to run the program. So I'm going to go ahead and actually load in the network already built. So this was built earlier, but I went through that same process. And so there's the network already built. Let's see if I actually was interpreting my drawing of the tank correctly. Indeed, I more or less was. So now we could run the simulation. For example, if we go to junction 5, it has the demand in. Unfortunately, this one's in cubic feet per second. So we'll take this time. Let's convert it back into gallons per minute. So first we change the project back to gallons per minute. And we'll go ahead and change the demand. 1.11 cubic feet per second, I'm pretty sure is 500 gallons a minute. Yep, and then 2.2 will be 1,000, and then 2.6 or something will be 1,500. So we enter the 500 gallons per minute, move to the next node. 500 gallons per minute, move to the next node. 500 gallons per minute, move to the next node. That's 3, so 1.1 is 500, so that's 1,500. Move to the next node. That's going to be 1,000. Move to the next node. That'll be 1,500. And we've essentially entered the data for the network as presented in the PowerPoint presentation images. And now we would run it. And we can run it either by choosing the lightning bolt or project run analysis. And we got the always desirable okay, so our run was successful. Again, doesn't mean it's correct, but it means it was able to find a solution. The data were consistent with hydraulic modeling. It found an answer, and it's now reported it. It's showing the flow directions, which actually makes sense. So all the water is coming from the tank and distributing through the network based on the demands. And if we turn on the pressure and start looking at pressures, we see that the lowest pressure is at junction 3. And it's important that we are aware that that's a pressure. So that's total head minus elevation. If we were to look at, instead of pressure, head in the system, node number 3 does not have the lowest total head. The lowest total head is going to be node number 6, which should make some hydraulic sense because it's hydraulically the farthest distance from the supply point. But our statutory requirements in our design guidelines usually stipulate pressure and not head. And we can examine the flow values by turning them on, and we now have the flow rates in gallons per minute. So let me ask you all a question. We have a negative value in pipe 1 and a negative value in pipe 6. And so what's the resolution for those minus numbers if we have a client that doesn't like minus numbers? So there's a property called reverse. And so we can reverse the connectivity. The moment I touch that, I just made it wrong, and it's been indicated by this has turned to a black marker. Let me rerun the simulation. And now we get it as showing flow coming out. So that's now a positive number. The direction in terms of what's presented by the arrow doesn't change, because after simulation the arrows always point in absolute flow direction. We can reverse the connection of that one, rerun it, and now we have positive numbers. And what we did when we pressed reverse is we simply interchanged the values of the starting node and the ending node. So that pipe starts at node 2 and traverses to node 1. And this pipe here starts at node 5 and traverses to node 4, I'm pretty sure. Yep. And that's how we resolve negative numbers that we don't like. The numbers are correct. The minus sign in the flow simply means the stated connection direction is opposite of what it should be to produce a positive result. So we'll move on to the next example. And in the next example, we're going to add a pump. This particular slide right here is showing the effect of plotting friction factors. That'll be expressed at the link. And so these are computed values, and these are the friction factors for the different pipes. And we could do a little trial and error to try to get these numbers to agree with the ones in the original table. But I won't do that in the demonstration. We also can generate a status report. We do that in the program by choosing report. And we have a choice of status, energy, calibration, or full. So we choose the full report, hit save, we'll overwrite the existing one, and then to look at the report, we would open it up in a text editor. And in the text editor, here's the output report. It tells us the run date, what we were using for input file. It gives us the the connectivity table for each individual link or pipe, if you will, starting node, ending node, the length and the diameter. We can append the output. We can have it print different columns, but we have to do that before creating the report. It also reports the individual nodes. So nodes 1 through 6 plus 9, which is the tank. And tanks and reservoirs are explicitly identified in the report. And it has the supplied demands for the nodes and then a computed demand in the case of a tank or a reservoir. And the various heads at each location, and then the pressure in pounds per square inch. And then for each link, the whole point of doing the simulation was to get the flow rates in each link. And so we have the flow rates in gallons per minute, velocity in feet per second, and head loss. And we observed something interesting that in pipe number 8, the flow rate is 15 feet per second, which is a bit high. That's what it has to be hydraulically, so that would be an indication to us that we might want to use an even bigger diameter. We already got a 24-inch somewhere in the network. It wouldn't kill us to make a 24-inch for this pipe. And so we've just viewed these already. A quick remark, the problem was given in gallons per minute, and I actually changed it from the old cubic feet per second into gallons per minute. The velocity in the pipe from the tank is 15 feet per second, which is somewhat higher than one would want. That would be, we would logically consider a larger pipe or some sort of flow control valve, which wouldn't help very much, to try to keep that velocity something more in lines with 2 feet per second to 10 feet per second. These higher velocities are problematic when we have to change the pipe flow direction. because there's going to be a lot of momentum in that pipe. And if you recall, momentum is the product of mass and velocity. As the velocity is too big, the amount of force required to keep a pipe from moving is fairly substantial. So we have pretty large thrust blocks in these high flow rates. Plus, if the pipe does fail, that's quite a bit of water coming out real fast. So you have trouble drinking it up and cleaning up the puddle. So moving to our next example, which I believe is going to be example 4, we're going to examine pumps in EPANET. So the key things to know about a pump when we're trying to simulate its behavior in the EPANET model are that pumps are a type of link. So pumps are modeled as links between two nodes, and the pumps will have pumping curve properties assigned to them. Each node that connects to a pump should have appropriate and realistic elevations. The default elevation when we create a node is 0, so the analyst would have to remember to check the inlet and outlet elevations to put them at the correct values that make sense for the situation. And then the pump is added as a link, and then in the data browser we select an object called a curve, and we enter pump curve information, and then we will associate the pump curve with the particular pump link. The program will operate the pump out of range in order to get an answer. That's what it's designed to do. But it will issue a warning to us in that situation that the pump is operating out of range, and that is guidance that either we have conceptualized the problem somewhat wrong, or we need a bigger pump. So returning to our example, the one we're going to want to use is example 4. So let me go ahead and create a new project, load in a backdrop, and we'll load in example 4. So there is our example that we're going to do, and now let's continue with the presentation. So the figure is a conceptual model or diagram schematic of a pump lifting water. We're told it's a 100 millimeter diameter, 100 meter long, ductile iron pipe, and we're moving water from a lower reservoir to an upper reservoir. Not very far, 10 meters, about 30 feet. The suction side of the pump is a 100 millimeter diameter, 4 meter long ductile iron pipe. So this portion of the system right here is 4 meters long, but the distance from the water surface to the inlet is 3 meters. And that puts the suction pipe 1 meter below the top of the water surface, which makes sense. That means there'll be sufficient suction head for it to work well. We're told the difference in the free surface elevations, the pool elevations, is 10 meters. And we're given a pump performance curve that says that the added head of the pump is equal to 15 minus 0.1 multiplied by the flow rate squared, where the added head is in meters and the flow rate is in liters per second. Our goal in this case would be to, from these conditions, if we turn the pump on and it comes to equilibrium, what's the flow rate in the system going to be? I happen to know it's around 6 liters per second. So here's the base diagram, and here's the pump curve. So we would follow our protocol again, sketch it out on paper, identify the pipe diameters, length, and roughness, identify the node elevations and demands, the supply reservoir or tank and its pool elevations, and then identify pumps and prepare a pump curve and problem units. So there's the layout on paper, and if I actually had that graphic in an uploadable form, I would use that because that has everything I need to know on it. But that's our basic layout. And then we would supply the pipe parameters. So pipe 1 is 4 meters, 100 millimeter, 0.85. Pipe 2 is 100 meter, 100 millimeter, 0.85. And the 0.85 is derived from this table. Roughness coefficients for new pipe. And I actually don't know where that's from. It obviously is taken from a book somewhere. Then we'd identify the individual node elevations. So we have node 1 at 3 meters, node 2 at 3 meters. So those are the nodes that we're going to connect to each other with a pump, and then we'll connect each of these nodes to their respective nearest reservoir. The pool elevations are specified, so we use 0 and 10. We could just as well use 90 and 100. It's the difference that matters. And lastly, we have to prepare some pump performance data to enter into the program. We cannot enter an equation. As far as I know, it doesn't have the capability of accepting an equation like that and using it. But what we can do is take 3 points from this equation and supply the 3 points. And so in this case, you should always supply shutoff because usually you know that. So if the pump produces 15 meters ahead, it does it at almost zero flow rate. There's very little flow through it. 12.5 meters ahead, we get 5 liters per second through the pump. 5 meters of added head, we get 10 liters per second. So we can use that information to enter a pump curve into the program. So now I'll switch back to the program, and we'll go ahead and build this quite quickly. This one I actually will build live. So we set the project defaults, hydraulic properties. We want this to be in liters per second, Darcy-Weisbach. So our base is set up. We have 2 nodes, one here and one here. And I'm just putting them there for drawing reasons. And each of those nodes has an elevation of 3 meters. And we have a need the reservoirs next. There's a reservoir. There's a reservoir. We'll set the elevation of each of the reservoirs. We'll make this one elevation 10. This one elevation 0. So our reservoirs are set up. And now we will connect them by pipe to each of these nodes. And if you want to follow the curvature, you can, but for this example, I'm not going to bother with that. And next we have to add a pump, and the symbol for a pump is this guy right here. And our pump is entered. We'll now go parameterize our pipes. So that pipe is 100 meters long. The diameter is stated in the problem as 100 millimeters. And I think the roughness height is 0.85. Now we go to this pipe, which is 4 meters long, also 100 millimeters, also roughness 0.85. So now we've built the physical representation of the network. but we haven't provided the pump curve. I'm going to go ahead and run it so I can show you what the error looks like when you forget your pump curve. Unsuccessful, so it tells us we're failures, and it says no head curve or power rating for pump number 3, one or more errors in the file. So to correct that, we go here into the browser, choose the Data tab, and choose the curve object. And we want to create a curve, and it plonks at me. Oh, is it not working mode all of a sudden? Let the network catch up. Okay. We're going to have to terminate the program and restart it. Something has gone wrong, and that is common given that we're running this on a remote server. So let me figure out how to stop the program real quick. 21047, I think is the program ID. Yep, I guess right. We'll just relaunch it. So a habit to get into if you're using this environment is to save the project from time to time before you commit to stuff like running it. So let me go ahead and open the project, because what we just built there is lost forever. But we can get the old copy. So here's the old copy. And the only thing I'm going to do is interesting. Oh, my bad. Curves, there we go. So there's a pump curve, but I'm going to go ahead and actually delete it. Okay, so here's where we were last time. So if we run the program, we get the error, and same thing, undefined pump curve. And so now we need to add a curve and choose this button here to add the curve, and we can start to build the pump curve. We know that at 0 flow, we get 15 meters of head. We know that at 5 units of flow, we got 12.5. And I have to go look at the other one. 10 units, we get 5. At 10 units of flow, we have 5 meters of head. and it can fit a curve through 3 points. And so there is the equation that represents the curve that's fitted through the points that's identical to the input curve. That won't always be the case. Often it'll just be close. But in this instance, it's identical. Choose OK. And now the pump curve exists. We go, OK, it's going to work. But the run was successful, and that's because the pump was associated with pump curve number 1. And this guy is hiding because it likes to hide. We turn on head and flow. And other than pretty colors, until we tell it to actually render it in notation, so we'll display the values. And now we have the flow rate is 6.37 liters per second running through the system. The pump at the suction end is has a head of slightly less than 0. And remember, the head in this reservoir is 0, so it has to be slightly less to get there. And on the discharge side of the pump, it has a head of a bit more than 10 meters, 10.91 meters. If the roughness in the pipes was much different, so we'll go up 2 orders of magnitude, rerun the simulation. We'll see that we can't get as much flow rate, and we need to produce more head at this node to push water up into the upper reservoir. And so in this instance, that's the limiting case. I'll put it back to the value that was there before. And 6, okay, that's about right. So that concludes this example. Our last example will be a network with a pump. And in this last example, we have a pump is installed in an 18-inch pipe that extends from a ground level reservoir and boosts it into a network. And we want to find the discharge and flow connect direction in each line and pressure at each junction node. It's the same kind of problem. Again, the same modeling protocol, layout on paper, pipe diameters, node elevations, supply, pumps, sketch the layout. Everything in blue we already have done. And so all we're doing is adding a few more pipes in this new reservoir and this new pump. So the new pipe information is contained in this table. Pipes 9 through 14, their length and diameter are given. And the 3 new nodes, that information is given. And the pump curve is given in this table. And it has values of added head in feet, 200, 175, 110. For different flow rates. Shut off, 10 cubic feet per second, 20 cubic feet per second. You notice that cubic feet per second and gallons per minute are not the same units. So our options would be we could stick with the pump curve in cubic feet per second, in which case we would have to change the demand in 9 nodes from gallons per minute to cubic feet per second. Or we can change the pump curve, which involves only 3 unit conversions from cubic feet per second to gallons per minute. So only an idiot would change the node values, so that's what I did the first time I ever did it. But instead would change the pump curve. So we would build that prior to actually constructing the model. And here's the model, and we're going to go look at it in the actual software. So in this case, I'm going to open the already built model. There's not much new in this example in terms of specialized data entry. stuff. Well, actually, there is a little bit new, but there we go. Sure, we'll save the results. So there's our network, and if we want to, we could attempt to load a backdrop. I think I have one for it. There's the backdrop. Not much to be gained in this case. But if we were first drawing the network, then by all means the backdrop would be useful. I want to point out a couple of interesting things here. So I have a junction there, and a junction there, and then everything's boosted into the network. This is my personal preference in how one should model pumps in the system. You should create 2 nodes just for the pump, rather than do the lazy way, which would be to go straight from the reservoir to this node and then through the 900 feet of pipe or whatever it is to get into the system. The flow answers will be the same, but I feel that this is a superior way to conceptualize these problems. So let's look at these 2 nodes. They're both at elevation 155. They have no internal demand, and their main purpose in life is to connect this reservoir, which has a very large diameter pipe, and into the pump, and then connect the pump here through a short, smaller diameter pipe into the network. Everything else is the same as in the prior 2 examples in terms of data to enter. So we would provide elevation, any demand. This one's in CFS, so let's hope the pump curve for this one is in CFS. Yeah, whoever did the pump curve left it be. That was me. So that means I converted 9 nodes from gallons per minute to cubic feet per second. That's not the brightest move I've made, but it's correct. I mean, it will work. So we run the simulation, and we now have the total head at each of the nodes and the flow rate in cubic feet per second throughout the system. It's also giving us flow directions, which at times are useful. And that concludes this example. What we're going to pick up next time is a little bit more on dealing with tanks. But just for grins, let's look at a system of more realistic scale. So I may have shown this earlier. I think that's the right one. Okay, so here is a more typical scale of a practical EPANET model. There's a whole lot of nodes and pipes in that picture. And so when we run these kind of models, all of a sudden the naming convention becomes really important. And I'm going to turn off the backdrop. And so there's a network we want to simulate. Now when we go ahead and run it, it does its running thing. And this one I think is a time-varying simulation. So there's a reservoir here, and there's a storage tank right there. And so we're now letting the simulation play back each of the time steps. All I want you to do is see stuff is changing in this picture. There's no intent that any individual number means much at this point. So it's just running loop after loop of simulation, or we can produce time series. And what we want to do is, see, that's a node. Oh, go ahead and do head at that node. And so in that node, at about hour 7 of the day, the tank starts to draw down, then it builds back up again, draws down, builds up again, and then returns to this steady case. So that concludes the lesson for today. The next time we'll talk about more about tanks and reservoirs. So if there are no questions, I'm going to go ahead and end the Zoom call. I want to wish you all a great weekend.
What's the best way to turn an image into the BPM file?
It's called bitmap. You would use software that would convert whatever image you want into a bitmap format. There's probably different programs on the internet that can do that.
Okay, thank you.
Windows Media Viewer can probably handle it, stuff like that. So if there's no further questions, I'm going to go ahead and end the meeting, and you all have a great weekend. Bye-bye.